Hello and welcome to this series of lectures covering satellite-based SAR and InSAR. My name is Jon Leighton. My original background was geodesy and surveying, but I've been processing SAR data since about 2004, firstly with the University of Nottingham, and then with 3V Geomatics in Vancouver since 2012. These first few lectures focus on satellite-based SAR, which is a data source and stands for Synthetic Aperture Radar. Lectures discussing InSAR will follow after. InSAR, or interferometric SAR, is a loose umbrella term for a range of processing techniques applied to SAR data, in our case to isolate ground displacement. After a brief look at the history of radar, we're going to look at past, present, and future satellite SAR systems. We're going to contrast active systems like SAR with passive systems such as optical satellites. Then we're going to look at how satellites orbit and why that's important for the data. And then we'll discuss the basics of the SAR signal and the interactions with the ground and why, for instance, topography can cause some issues. This slide presents a brief history of not just SAR, but radar in general. In 1904, Charles Hulsmeyer first demonstrated ship detection, but without ranging, so not strictly a radar, which stands for radio detection and ranging. In World War II, the potential applications for radar were clear. Several nations worked on this separately, arriving at various breakthroughs, and collaboration between them provided what we now recognize as a working radar. SLAR, or side-looking aperture radar, was an early imaging radar and a precursor to SAR. It had excellent resolution in one direction, this is the direction that it looked, called the range direction, but not in the direction that it flew, called the azimuth direction. So it had to fly quite low to achieve reasonable resolution overall. But this limitation was solved in the 50s by Carl Wiley of the Goodyear Corporation, which for the first time made possible the concept, at least, of putting a radar in orbit. This predated satellites and the processing power needed for such a task, but it was finally realized in 1978 with NASA's CSAT mission, which was a proof of concept more than a system generating high volumes of data. Then in the 90s, a series of European and Japanese missions brought SAR data to a much wider audience. Since the 2000s, several other SAR systems have been launched, and we are now seeing small SAR constellations of 2 to 4 satellites, but larger constellations of 18 are either in planning or being commissioned as we speak. This is the timeline of SARs up to the present and beyond. It's split into radar bands. X is the shortest wavelength, shown in blue. C is twice as long, shown in purple, and L-band is the longest, shown in green. Shorter wavelengths have higher frequencies, and higher frequencies are more easily scattered. Consider a noisy neighbor playing music through the wall next door. The thud of the low frequency sounds penetrate through the wall, but the higher frequency detail is lost. This is the same with SAR. When vegetation is present, shorter wavelength SAR data is scattered, and longer ones can pass through, reflect, and return back to the sensor. Let's look at this chart now and see some of the notable satellites, particularly for geotechnical monitoring. In the X-band section is the workhorse for mining InSAR, TerraSAR X. This is actually a constellation of 3 satellites now, providing high-resolution data with a short repeat of a few days and easy data access. Other X-band systems include the Italian Cosmos SkyMed constellation of 4 satellites and a future constellation of 18 sensors called InSAR. Currently, 4 of the constellations are already in orbit. In the C-band section, most notably is Sentinel, a pair of satellites providing free data globally, often as far back as 2014. So there is guaranteed historic SAR data covering every mine in the world, typically for years, and anybody can access it and process it with the right know-how. L-band data at the bottom is useful for monitoring in the forests of Alberta or the jungles of Indonesia. It's important to note that while it's less sensitive to vegetation, it's also less sensitive to pretty much everything else, including ground displacement. But often it's the only viable choice. Let's take a closer look at TerraSAR-X. This is a German system launched in 2007, capable of 11-day repeats, later joined by a second and then a third Spanish satellite called PAZ. This offers repeat times now of alternate 4 and 7-day gaps. 3-meter data is typical, but it's possible to get higher resolution at the expense of a smaller footprint. Sentinel, launched in April 2014, was initially capable of a 12-day repeat. Unlike other sensors, Sentinel is basically always switched on when over land, so it's constantly collecting data, and large stacks of data are available anywhere except Antarctica. Other sensors like TerraSAR-X only collect data when they are tasked. So Sentinel is more like GPS, pretty much always on. 2 satellites are now up, offering a 6-day repeat, and with plans for more satellites to follow. Because the data is free and open access, it raises interesting questions about privacy and liability. All kinds of displacement events like earthquakes or slope failures often result in a race to be the first to post results leading up to the event on social media. ALOS 2 is a Japanese L-band mission launched in April 2014, capable of a 14-day repeat. It offers high-resolution data but lower precision displacement results due to the nature of its longer wavelength, which we'll talk more about in a future lecture. Getting data can be a little tricky. Lots of the satellite's time is set aside for scientific purposes and Japanese national interests.